All right, folks. So today we are wrapping up, as I said before, Unit 3. We are talking about L'Hopital's rule and indeterminate forms. So what this is going to allow us to do, if you are given or you have an expression that you are evaluating the limit as x approaches some given value, and when you use direct substitution, you end up with 0 over 0 or infinity over infinity. Okay, this is known as the indeterminate form. One thing that I do want to point out here is that your indeterminate form could also be negative infinity over negative infinity, or negative infinity over positive infinity, or positive over negative. It doesn't matter. That's still considered an indeterminate form. So you could have negative infinity over negative infinity. You could have negative over positive. I mean, it doesn't really matter. Okay, it doesn't have to be positive over positive, negative over negative. It's still indeterminate. And what L'Hopital's rule allows you to do is convert the given indeterminate form into a limit that you can actually evaluate. But this rule is very specific, and you need to make sure that you are paying attention to what you are doing. This is only when you are evaluating a limit. Okay, this is only when you're evaluating a limit, not when you are finding the derivative of a quotient. So you need to make sure you're paying attention when I go through this. Okay, so what they're saying here is that if you plug in whatever your a value is as x is approaching that value to your function f and to your function g, and you get 0, and if you can evaluate f prime of a and g prime of a, and as long as the derivative of your denominator's function evaluated at that value is not 0, then basically what this is saying is, in order for you to evaluate the limit as x approaches a of this given quotient, you can take the derivative of the top independent of the derivative of the bottom and then resubstitute. Okay, so let me go back and just kind of review limit rules. So when you're evaluating the limit as x approaches any given value, okay, our rule of thumb is that what we want to do is be able to use direct substitution first. If we cannot use direct substitution, what do we look at next? What do we try? Yes, we try to factor. If we can't factor, what else do we look at?
Complex.
Complex fractions, so we would simplify any complex fractions. There's one more. What else? Yes, rationalize. Way to go, Jay. Okay, so if we are stuck, meaning the limit as x approaches 0 of the sine of x over x, we did that in Unit 1, and we had to evaluate that limit by using a calculator. Okay, now using L'Hopital's, what it lets us do is attempt direct substitution, which obviously doesn't work because what's the sine of 0? What's the sine of 0? 0. Oh my gosh. And then when you plug in 0 for x, you get 0 over 0, indeterminate. So at that point, we were kind of stuck because we couldn't factor anything or whatever. What L'Hopital's allows you to do is then, once you have used direct substitution and determined that you have an indeterminate value, you then want to evaluate the limit as x approaches, I'm using this example, 0, take the derivative of the sine, take the derivative of x, and reattempt direct substitution. Then you can actually evaluate the limit as x approaches 0. And we have some examples, and actually the examples right here that I'm talking about. What I want to do first is go through some of these concepts and just make sure everybody understands these are just concept checks. This is not actual division. This is a concept check. So here, we're taking a look at if we are taking 0 and dividing it by any number, what do you get? 0. Positive or negative, it's still 0, right? If you take a number and you divide by 0, stop. I know you can't divide by 0, but the idea here is you are getting really, really close to 0, meaning 0.00001. You're approaching 0, I don't know, from the right or from the left. If you take any number and you divide it by a very small number that's close to 0, what do you get? A big or a small number? Ben just went like this. Huge! You get a huge number. Does anyone have a calculator out? This is calculate your brain. Oh my. Okay, so J, calculator J. Just do me a favor. Take 10 and divide it by 0.0001. Not J.
It's like 100, 1 million.
1 million. Okay, so do me a favor. Take 10 and divide it by 0.0001. Make sure I added one more zero in there.
1 billion.
The first one I did 4 zeros.
Okay, do 5.
Okay.
Is it even bigger?
Yeah.
Okay. So as Ben said, it becomes huge. Ideally, what we're talking about here is, as we take any number, whether it's 10, 5, 1, okay, and we divide it by a really small number that gets really close to 0, it's going to be a huge number. What do we use? Infinity, exactly. So this answer would be infinity. What if we take a negative number and do the same thing? Negative infinity is what we're going to get. Okay, this is a concept. You need to understand conceptually what's happening, because you're going to get, I don't know, let's say as x approaches 0, you need to understand you're approaching 0. You're getting close to it from one side or the other. So what is happening? Here, we take any number, positive or negative, and we divide it by infinity. Okay, can we divide by infinity? So then conceptually, what am I telling you to do?
Divide it infinitely.
Okay, Sir Isaac Newton. Yes, I am looking at a huge number in the bottom. So I could take like 1 and divide it by 1,000, and it's going to become very small. So what will that value approach? 0. Got that, Newton?
Oh yeah.
Okay. Questions? This is really important to understand conceptually. All right. So as I stated before, what we're taking a look at here is, whenever we are evaluating a limit, we want to try direct substitution first. I want to see your direct substitution on your paper. I want to see it. Okay, because I want to understand that you understand what you are doing. So in this case, if we were to evaluate the limit as x approaches 0, using direct substitution, when x is equal to 0, we've got the sine of 0 over 0. What's the sine of 0, you told me? 0 over 0. This is indeterminate. So now what we're going to do is we are going to use L'Hopital's rule. So we need to rewrite the limit as x approaches 0, and now we take the derivative of the top, which is what? Cosine of x, over the derivative of the bottom, which is, okay, let's pause here for just a second. This is not the use of the quotient rule. And if you were asked to take the derivative of this, you cannot use L'Hopital's. Does everyone understand the difference?
Yes.
L'Hopital's is reserved for when? Limits, exactly. Okay, now again, you try direct substitution. Direct substitution, x equals 0. We've got the cosine of 0. What's cosine of 0? It is 1. If you recall, when we evaluated this using the table in Unit 1, we approached 0 from the left and 0 from the right using the table function, and we did get 1. Okay, but now you should be able to do this algebraically. Questions? That's L'Hopital's. Okay, so let's look here. We want to evaluate the limit as t, or x, or whatever your variable is, approaches 0. First thing we want to try is direct substitution when t is equal to 0. So we've got the square root of 4 plus 0 minus 2 over 2 times 0. Okay, yeah, it's 0 over 0. Because this becomes the square root of 4, which is 2, minus 2 over 0. Okay, so now what we want to do is actually take the derivative. So we can do this a couple different ways. We can rewrite this in friendly form, or we can actually use the derivative for the square root of x rule. So if this right here, this whole thing is my x term, and I have the limit as t approaches 0, I need to take the derivative of this part. What's the derivative of the outside? This is a chain rule. What's the derivative of the square root of 4 plus t? I heard it a little bit louder. 1 over 2. That's perfect. Okay, then I have to take the derivative of the inside. What's the derivative of the inside? Yeah, it's just 1. So that's the first part. What's the derivative of negative 2? 0. Okay. So now you take the derivative of the bottom. What's the derivative of 2t? 2. Okay, before I continue, does everyone understand how we took the derivative of the top and the bottom independent? Okay, now we want to try direct substitution again. So this is what we have when t is equal to 0. We've got 1 over 2 times the square root of 4 plus 0 all over 2. Okay, all I did was plug in so that you could see it, direct substitution. So this becomes 1 over 2 times the square root of 4, which is what? Yeah, you could answer this 2 different ways because it's kind of a, yeah. What's the square root of 4 times 2 is? And then when you divide it by 2, isn't that the same thing as multiplying by 1/2? So what is this overall answer? Is 1/8. Now, you wouldn't have gotten that answer algebraically. You would have had to have used a calculator. What's another way we could have dealt with this? Anyone know? Tried. It would have taken longer. How did they get the radical in the top? What did they do? Oh, they rationalized. So remember, you unrationalize. If you remember in Unit 1 when we were talking about limits, it kind of didn't make sense to us because in pre-calc we were trying to get the radical out of the denominator. Then when you want to evaluate the limit, you actually put it back in, which seems to make no sense, but it kind of makes things go away. Questions? Okay, let's take a look here. We want to evaluate the limit as x approaches positive infinity of the natural log of x over x. So if we try direct substitution when x is equal to, we know infinity, really this is just a humongous number, right? We end up with the natural log of infinity over infinity. What's the natural log of infinity, you think? Yeah, it's a huge number. It's just a big number, so this is going to be infinity over infinity. So this is indeterminate. So now what we have is the limit as x approaches positive infinity. Remember, you have to rewrite that. What is the derivative of the natural log of x? It's 1 over x. Over, what's the derivative of x? Oh, okay. Just 1 over x, right. Okay, so now this is why I went through the concept check. When I go back and try direct substitution, ideally what we have is 1 over infinity. Well, that's an infinity. But what this means is I'm plugging in a really, really big number. What is 1 divided by a humongous number? 0. It is 0. Questions? Are you sure? Okay, so let's take a look here. So far we've talked about and looked at variables x, t, j, k, whatever. What's theta? Is it a variable? Yeah. So it just is in reference to an angle, whether it's in radians or degrees. So we want to try direct substitution when theta is equal to pi over 2. So we have pi over 2 minus pi over 2 over the cosine of pi over 2. This is 0 over what? Yeah. Okay, so this is just showing me I cannot use direct substitution as is. So now we will use L'Hopital's, the limit as theta approaches pi over 2. What's the derivative of theta? Yeah, 0 goes away. What is the derivative of negative pi over 2? Wait, what's the derivative of this? It's 1. Okay, so this is 1 minus 0, or 1, over, what's the derivative of the cosine? Negative sine. Ooh. Whoa. Okay, so basically what we have is the limit as theta approaches pi over 2 of 1 over negative sine of theta. What do I do now? Yeah, try direct substitution. So we've got direct substitution when theta is equal to pi over 2. So this is 1 over negative sine of pi over 2. What's the sine of pi over 2? 1. So what's my answer? That's right. Okay, questions on L'Hopital's. This is pretty direct right here and how you use it. But remember, after each time, you must try direct substitution. Okay, so what this next part is telling me is that if you get an indeterminate form again, meaning the first time I use L'Hopital's and I try direct substitution and I plug my values in, and I get an indeterminate form again, I actually can apply L'Hopital's again. So L'Hopital's can be repeated as long as you do direct substitution after each time you take the derivative. Don't look at the problem and say, oh, you know what, I think I'm going to do L'Hopital's 3 times. Okay, that's not how it works. You need to try direct substitution, see that you get an indeterminate form, then you would try L'Hopital's. It is possible, folks, that you could have a problem that looks like you cannot use direct substitution, and when you do it, it actually works. So you need to be careful. You should always try direct substitution first, okay, even if you think you can't. So when I take a look here, I need to evaluate the limit as x approaches infinity. What's going to happen here? When I use direct substitution, I do get infinity, because when I take a huge number and I cube it, huge-er, times 5, even more huge, minus that big number squared times 4, still infinitely large, and then, oh wait, let me just add 1 to that. So already with direct substitution, when x is equal to infinity, I've got a humongous number on the top, and then based on that pattern, you can see that on the bottom, you're still going to have infinity. Okay, yeah, I know you could probably look at it and say, fine, that's what's going to happen. But this problem, I just want to show you that there are 2 ways you can evaluate this. Some of you might already see the one way, but I'm going to show you using L'Hopital's first. So we have the limit as x approaches infinity. Okay, and we're going to take the derivative of the top and the bottom independent. So this is what? 15x squared minus 8x over 21x squared plus 2. Is that right?
Yeah.
I tried direct substitution here, where x is equal to infinity. We still get infinity over infinity, right? Still a huge number, okay, and indeterminate. So we've got the limit as x approaches infinity. Try it again. 30x minus 8 over, what is this, 42x? Okay, try direct substitution again. Still indeterminate. So you have the limit as x approaches positive infinity. This is 30 over 42. Is that right? Okay. What happens when you evaluate a limit of a constant, regardless of what x is approaching? What's your answer? Yeah, it's the constant value. It's the limit as x approaches infinity of 30 over 42. The limit as x approaches 1 of 30 over 42. It doesn't matter, because the answer is still going to be whatever this is, which in this case reduces by, what, 6? 5 over 7? Okay. So that kind of seems like we didn't use direct substitution, but let me also remind you that when you're evaluating the limit as x approaches infinity, you can also use the horizontal asymptote rules. So this was one just designed to show you that you can take the limit as many times as you need to, the derivative as many times as you need to, but you have to evaluate the limit in between each one. I would have gone with the horizontal asymptote rules because it's faster. Yes?
Would you have to still show, like, you wouldn't have to derive the original problem, like, if you knew the horizontal asymptote?
Yes, no. If this did not give specific directions, like, say, evaluate the limit using L'Hopital's, okay, if it just said evaluate the limit, and you recognized right away, oh, well, the degree, first of all, it says x approaches infinity, right? If this was as x approaches 0, you could use direct substitution right away, right? So you really need to think, just use direct substitution first. But if you recognize that, absolutely, if it doesn't tell you what to do. Questions on the first one? So either way, we still get 5/7, right? Still the same answer. Okay, in B, this is the limit as x approaches infinity of x to the 50th power over e to the 2x. So if I use direct substitution where x is equal to a humongous number, what is this humongous number to the 50th power? Unfathomably large. Agree? Like, I can't even think about how big that number is. Okay, and then when we take e, which is, what, 2.7 and change, and we take that to the 2 times this humongous number, I've got infinity over infinity. Agree? Okay, so let's use L'Hopital's. What we have is the limit as x approaches positive infinity of 50x to the 49th divided by, what's the derivative of e to the 2x? 2e to the 2x. Okay. So what happens when I use direct substitution? Yeah, I got nowhere really, right? So then I would have to, again, take the limit as x approaches infinity of 50 times 49 x to the 48th power over 4e to the 2x. Okay, before I continue, does everyone see how I got that 4? Because this is, the derivative of e to the 2x is 2e to the 2x times 2. Okay, did that really get me anywhere? Okay, so this is one now we need to think about what's going to happen.
Over and over again.
How many times, at least, in the numerator, how many times do I have to do it?
48.
48. Again, Sir Isaac Newton has returned. Okay, literally, from the beginning, I'm going to have to do this how many times?
A lot of times.
More specifically, though. 50! I have to take the derivative 50 times, right? So I can get rid of that x. So that means I'm going to have 50 times 49 times 48, 47, 46, 45. What's that called?
Factorial.
Nice, 50 factorial. So we have the limit as x approaches infinity of 50 factorial divided by. Okay, now, if I have to take the derivative of the numerator 50 times, how many times do I have to take the derivative of the denominator? Okay, definitely 50. So this one is 2 times 2e to the 2x. Agree or disagree? Okay, isn't this 2 to the second power then? Because the base is the same? How many would it be in the denominator here? 2 to the 50th power e to the 2x. Okay, this is conceptually what would happen if I literally did this. We don't have all day, right? I mean, you might, but I don't have all day. Okay, does everybody understand what happened here? Yes or no? Okay, now, Jay, no?
I mean, I get it, but
Okay, I would have had
get
to.
it.
That's what I'm asking. It's important that you do.
I would say I'm there. Essentially, I'm there. I feel like I'm being bombarded with humongous numbers.
Okay. If I had to take the derivative to get rid of that x, because each time I plug in infinity for x, I'm getting an infinity in the numerator, right? Whether I take it infinity to the first power or infinity to the 50th power, it's still a large number, conceptually, correct? Okay, so in order to get rid of this x, I have to take the derivative of my original term 50 times to get rid of the x. That's where 50 factorial is from. Now, if I have to take the derivative of the top 50 times, you're going to have to do the same thing to the bottom, because the bottom's just tagging along. So that means I have 2 times e to the 2x. Then the second time I have 2 times 2 e to the 2x. The third time is going to be 2 times 2 times 2 e to the 2x. I have to do that how many times? 50. So it's 2 to the 50th power. So when I try direct substitution here, 50 factorial, it's going to be a big number, but it's not an infinitely large number. Agree? Because it's going to end at some point, right? Meaning it's got a solid value. When I plug in a huge number here, I've got 2 to the 50th power. Is this big or small?
Large.
Large, right? And then e to the 2 times infinity. Infinitely large. So that means I basically have 50 factorial, or a number divided by infinity. Go back to the top. What is a number divided by infinity? Look at your concept check.
0.
Does that make sense?
Yes.
Because you have 50 factorial divided by infinity, which is going to be 0. Okay, I went through that explanation because you need to understand conceptually what's happening here, because you could... You have to understand what's going on.
Gotcha.